Hi everyone, welcome to another session on AI ML for the product leaders. The agenda for the today's talk is Inference Engine. Inference Engine will be talking about by taking the illustration from one of the engine very widely used across the industry called vLLM. It's an open source project. We'll understand the importance of the inference engine, why it's relevant, why it came into picture, and what are the problems we are intending to resolve by using vLLM. We'll be talking it into different perspective in the CPU and the GPU specific machines. We'll talk about the pros and cons of using the inference engine across the two systems. Before we deep dive into detail, we need to set the background to understand what exactly we are going to talk about today. So let's hop on to the details. So before we deep dive into the pros and cons of the vLLM, here vLLM is one of the inference engine we are going to talk about. Let's understand what exactly it is. What the web server is for the web application is what vLLM or any inference engine is for the AI deployed models. Or in other words, once the model has been trained and we want to release it for the public use, we need to deploy it in one of the servers we have. We expose it through a server. However, in the real time, we see many constraints, and to be very precise, we see a latency and the throughput as a major issues that we need to resolve. And for the resolution, we talk about the inference engine. So when we talk about vLLM, it's basically that will scale the LLM inference, makes it faster, leaner, and cheaper. It will address the latency issues. Also, on the memory constrained devices, we'll see how we can leverage the same architecture and we can increase the throughput for our deployed model. So first of all, we need to understand why LLM inference is slow and expensive. What is the technical bottleneck we see around the same? For any LLM model, each token that is used to identify the question being asked to a system is determined based on its subsequent and previous token that comes into the query as such. Now, since there is a sequence evaluation and there is no parallelism happen, so at one particular moment, or we say for a particular second, only one model is being addressed by the model itself. So for one token, it need to undergo all the billion parameters the model has been trained on. Interchangeably, we can say as the number of billions parameters on which a model is trained, or more the accurate model is, more challenges would be with the response time from the model itself in the real time. Having said that, it's being noticed around 60 to 70% of the operation cost goes in the inference engine itself. Now we understand another constraint that we see in the current implementation, or when we don't use the vLLM, and what challenges the LLM inbuilt infrastructure poses us. We need to understand how CPU is being utilized. We see the traditional framework cause a random cherry pick of the memory locations from the system itself. Thus, most of the computer remains idle and thus increase the operational cost. Also, the caching is one of the mechanism that is not being leveraged as such. In other words, it keeps on processing the already processed data being taken in sequence. So we need to understand inference engine at the high level and increases the throughput by leveraging the key value caching, parallelism, and batch processing. So, at a high level, the underneath architecture for a vLLM here, when we talk about one of the inference engine, we are talking specifically about the vLLM. So, how does it resolve the issue? It leverages the technology underneath is a paged attention, continuous batching, and reduces the memory usage because the allocation of the memory is not given in a random but in a very pre-allocated manner. Hence, it utilizes the CPU compute to the best of its capacity. And also, it's using caching in parallel and allowing batching to happen, but not in a sequence, but in parallel aspect. Now, if you look at the architecture overview, we see a client send a request at the first stage. When the query is received by vLLM engine, we see it's getting scheduled, but it's getting scheduled through a batching. Now, when we are processing the request in the batch, it's increasing the throughput. Followed by page retention. Page retention is one of the mechanism internally optimizing the KV cache, wherein it stores the value and the or interchangeably we call the weight associated with the token in the internal data structure as a key value pair. Furthermore, the optimized attention and the decoding on the GPU causes a low latency. One of the constraints we see in vLLM or the inference engine is they are designed to be running on the GPU. They are ideal for the GPU, however, they can still be run against the CPUs. We'll talk about the constraint that it poses with respect to the memory constraint devices in the forthcoming slides. Before that, we need to understand what the business value the vLLM brings in. It lowers the operation cost up to 50 to 80%. Also increases the throughput. Hence, the real-time prediction, for example, for the fraud detection, specifically if we talk about, it has to be real time. And for real time, the system need to be having a low latency, should have high throughput. That is attained by using the batching mechanism of the vLLM or the inference engine. And thus it ends up with the better SLAs because the problems are being addressed at the very fast rate, and hence we have a better SLA. Just to summarize, it lowers down the cost, high throughput, and also increases the infrastructure efficiency because it improves the how the compute is being leveraged by using the allocation of the memory, not randomly, but using a precise manner on top of leveraging the KV cache for the pre-processing of the tokens. Now the question comes, how do we do the same on the local system or the system where we are having a restriction to use CPU but not the GPU? What are the trade-offs here? We see vLLM can be made to run on the CPU as well. However, internally it slows down the inference compared to GPU. For example, for the LLM models being trained on a billion of parameters ranging from 1 to 7 or 1 to 10, for instance, it's not suggested to use vLLM on the local system. However, if you are leveraging the benefit of light models, this can be used in local. And what benefit that brings in, we'll talk about that in the next slide. Now, before we get into the pros of using the combination of vLLM with the CPU, we need to understand what we attain when we run vLLM on GPUs. This is solely or the primary focus for using vLLM is to run on the GPU and the CUDA supported system. Moreover, this is for acceleration of the GPU based system specifically, thus it gives better result with the high-end parameter on the system with the high compute capabilities. Hence, it's ideal for production. When we are looking for the production related metrics, we indeed need to go for the GPU. But for the development perspective, to verify the API that we are going to develop and to do quick testing and the debugging, we can still leverage vLLM to use on the CPU itself. Now, if we see the quick vLLM inference API, we see, for example, we can leverage using Mistral 7 Beanstalk model, that's a billion parameter trained model, to understand the fraud detection, or we can generate the or print the model output for integration into the tools. And basically this could be confined to the embedded models also. For example, detecting the fraud using the chatbots as well. Now, if we do the comparison between the CPU and GPU level execution, we understand for the CPU it's very cost friendly because it has low upfront cost. We can leverage this for the development and testing for purpose. However, inference would be less because this is auto-tuned for the GPU execution. However, we can still leverage that for testing the APIs, for prototyping, and for early stage validation. Throughput though would be low, but we can still leverage and understand the configuration part for the KV cache and the memory limits. Now moving out to the GPU execution, it's basically tuned for the GPU and high infrastructure related or the compute capacity systems. Thus, with the GPU, it will give a significant faster inference and low latency. Throughput is very significant, and this is the ideal for the product development and wherein we need a demanding performance benchmarking. Now coming to where the enterprise should use a vLLM. Primarily, this can be used with the chatbots and AI copilots because we need to have a low latency response along with the fast retrieval for the large scale of the end users. Can be used for the retrieval augment generation, where for instance we are working more with the documentations and we need to do the retrieval at the fast rate using the LLM. And since this is something can work in batching and process, it's ideal for using for in the fraud detection pipeline where we need the real-time inference, that to at scale. And similarly for the compliance automation and for large scale personalized experience also, where we need a specific domain model is used, or we can say domain specific model, and we need a low latency for a customized and tailored use case. So if we see overall the takeaway for us why vLLM matters is it reduces the latency, lowers the memory usage because it's using page retention and the efficient cache mechanism. It has better GPU utilization, and thus it improves the SLA and also the cost saving. And basically overall it supports the development to production workflow because we can adapt and execute the vLLM across beta memory constrained CPU for development and testing purpose and validation of the APIs, or for the production ready workflow when we are leveraging the benefits of GPU compute power. So just summing up with the overall benefit that we can leverage by using LLM efficient architecture is basically it boosts the performances, cut cost, and also handles growing LLM workload. because we need to understand with the as the time passes, LLM gets trained over the large language, a large set of parameters, and hence the native capability of the LLMs to do the inference sequentially turns out to be bottleneck. Hence, we need to leverage the offering from the inference engines we have, that is to run in batching and in parallelism, leveraging caching at a high level. These are the bullet points we can put it as a benefit of using vLLM and inference engines. So basically our intention was to understand, once a person is done with development of model, how do we can evaluate in the real time. There are two prospects. While development, we can do the evaluation, we get the score, we train it against a specific data set. However, in the production, we need to anticipate how scalable it could be. Wherein the dependency, we have to bring it out to another library or the framework that's called the inference engine. That take up the that becomes the major load lifter to understand how to scale it using the benefits of caching, KV cache, and using parallel batching, and thus increasing the throughput for the AI models. This is all I had to cover in the current discussion. I hope it was helpful. We'll take up the new session on probably on the quantization and the distillation. That will talk. There will intend to cover how a large language models can be used when we have a constraint on the memory prospect, and still we can get the similar level of result for the prediction of our use cases. Thanks for being there. Thank you.